In this video, we're going to do a typical exam style question on linear programming. We're told two fertilisers are available, a liquid X and a powder Y. A bottle of X contains 5 units of chemical A, 2 units of chemical B and 1/2 a unit of chemical C. A packet of Y contains 1 unit of A, 2 units of B and 2 units of C. A professional gardener makes her own fertiliser. She requires at least 10 units of A, at least 12 units of B and at least 6 units of C. She buys X bottles of X and Y packets of Y. So we've got X, then we've got uppercase X, we've got lowercase y and uppercase y. We need to write down the inequalities which model this situation. Now the inequalities are the constraints. So let's pick up some information from the text. We've got now that X contains 5 units of chemical A. We've got that Y contains 1 unit of A. We're told now that she requires at least 10 units of A. If we now consider the text below, what we've got, she buys X bottles of X and Y packets of Y. So if we consider, if she buys X bottles of X, she will get 5X units of chemical A. So what we can say then is for A, and I'll just put it here, we're going to have now 5X. So say that she bought now 10 bottles of X, she's going to have 50 units of A. If we consider the next one, in Y, we've got 1 unit of A. So that's going to be lowercase y, plus Y. So if she bought 10 bottles of Y, she's going to have 10 units of A. This now must be at least 10. So we know that she wants at least 10 units of A. If we now consider the next bit of information for B, the first one, which is X, has got 2 units of chemical B. We've got here that the Y has 2 units of B, and we're told that we need at least 12 units of B in total. So our second inequality is going to involve the chemical B. So let's put B here. So what we've got here now is 2X plus 2Y must be at least 12. So we'll have now 2X plus 2Y must be at least 12. We can simplify that inequality to give us the constraint of X plus Y will be now greater or equal to 6. Okay, let's go ahead and consider now chemical C. And I'll just use a different colour here. So what we're going to have is 1/2 a unit of chemical C, and then we're going to have 2 units of chemical C, and that's got to be at least 6. So what we can say now is, now for C, this is chemical C, we can say that 1/2 X plus, now we've got here that the Y, let's just grab that up, has got 2 units of C, so plus now 2Y must be at least 6. So let's tidy that up and get an integer value. Multiplying through now by 2, we're going to have X plus 4Y will be at least 12. So there we go, that's what we've got. Now for these, we're going to have the non-negativity constraint. So if we consider now that X must be greater or equal to 0, and also Y must be greater or equal to 0. We can't have a negative number of bottles or packets. So we say X is greater than 0 and Y is greater than 0. So we need to write down the inequalities which model this situation. They are just here. In part B it says, on the grid provided, construct and label a feasible region. So let's think about what we've got. We've got these 3 inequalities just here. So let's just have this one. We've got this one right here. So 5X plus Y must be at least 10. We've got these ones just here. We've got the X plus Y must be at least 6. We've got now the X plus 4Y must be at least 12. And of course we've got our non-negativity constraints, which is going to form my axis here. So let's put these on, and I'll just grab this up. So we're going to have now the axis like so. So there's my y-axis, there's my x-axis. So let's consider a scale. Right now we know that we need to go up to 12. So let's go up to 12. So what's that going to give me? That's going to give me now, there's 5, there's 6. So we're going to have 12, which is going to be just here. So just slightly off. Okay, so there's 6, so let's put that on, let's put these values on. This is going to be 0, we're going to have 1, we're going to have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Ideally I want that on there, but never mind, we're going to have to deal with that. And then on this one right here, we can go up to, now we need to go to at least on this one 10, but we'll continue that upwards. So what we're going to have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we'll put up to 12, although we don't need it. Okay, so let's look at these inequalities. 5x plus y must be at least 10. So as we did in the last ones, what we're going to do is set x to 0 and y to 0. If you haven't seen those videos, please do check them out, as it will make some sense of what I'm going to do. So if y is 0, x is going to be here 2. So what we'll have then is 2, so let's put that there, x would be 2. 5 lots of 2 is 10. If x was 0, y would be 10, and that's going to be that point just there. So let's go ahead and we use a solid line now, as this is going to be now an inclusive inequality. So what we're going to do, we're going to go through the point just here and like so. So let's just tidy that up. So let's just make that look a little neater and make sure it's going through the points. With these small numbers, accuracy is really quite important, as often we're going to do this by testing now by observation. Often you don't, and they don't have to be as accurate, but testing by observation is going to be an option here. So what I'm going to do is label this line now, 5x plus y is equal to 10. Now we want this to be greater than 10, so we need to consider which side of the line we're shading. Quite clearly, if I pick 0, 0, that's not going to be bigger than 10, so we're going to shade now to the left of the line. The convention with this module is that we shade out the excluded area. So the excluded area, i.e. the values that don't satisfy this inequality or constraint, are going to be this side of the line. So let's just put that there. And of course your shading will be better. It's quite hard with this, but hopefully you'll get some idea. Okay, so that's what we're looking like at the moment. Okay, let's look at the next one, x plus y, and we'll draw the line x plus y is equal to 6. So what we'll have then is 6. So if y is 0, x is 6. If x is 0, y is 6. So again, a solid line to represent this constraint or inequality, and that will go through those like so. So now we can label this up, and again, it's ideally we want this to be accurate, as we're going to locate some values by observation. We can use some different methods, but I'm going to do this, I think, by observation. So what we can say then is that this now is x plus y is equal to 6, and that's that line right there. So we need it to be greater than 6. Again, quite clearly 0 is not included, so we want to the right of this line, so we're going to shade out everything to the left. Again, this is something that we looked at before, but if we test this point, 0, 0, is 0 plus 0 bigger than 6 or equal to 6? The answer is no. If we test a point here, 4, 6, if we consider now subbing that in, that is included in our inequality. So let's go ahead and just shade this out. So make yours as accurate as possible. Mine's not brilliant, but hopefully it'll give you some idea. So that's done. Now the next one is the x plus 4y is going to be equal to 12 when I draw the line. So we're going to have now x would be 12 and y would be 3. So when y is 0, x is 12. When x is 0, y is 3. And this is where my accuracy is going to go slightly off, as I'm going to now do this one here, and we're going to be over here. Now ideally I'd like to be a bit more accurate than that, but as my graph is not, my axis is not going that far, I'm just going to have to put up with a slight potential bit there. So let's do that and do like so. So let's put that on. It will give us some idea of what we're going to have. So there we go. That's what it's going to look like, give or take. Now we want this to be greater, and you can pick some points on this line. We want this to be greater, so let's just label this up. This is going to be x plus 4y is equal now to 12. So this is the line just here. We've got this line just here, and then we've got the line at the top. So all we need to do is shade now the feasible region. So if I consider that I want this to be greater, equal or greater than 12, then we're going to shade out the bit that we don't want, and again, that's going to be this side. If you test for point 0, 0, if x is 0, y is 0, 0 plus 0 is certainly not 12 or more. So we're going this side of things, and we can exclude all of these values like so. So that's what we end up with. So what we're going to do now is mark our feasible region R. So let's just put this on. Here's our feasible region R. So that's what we've got. Okay, we're now told a bottle of X costs £2 and a bottle of Y costs £3. Write down an expression in terms of X and Y for the total cost T. Now consider that we're buying X, and that's lowercase x, bottles of X at £2 a go. We're buying Y packets of Y at £3 a go. The total cost, and we can write this down, so we're looking at the total cost is going to be now 2 lots of X, let's write this in, 2X plus 3Y. So however many bottles of X we buy, it's going to be £2 a bottle. So say we buy 5, 10. If we buy 10, 20, and then £3 for every packet of Y. So if I bought 3, £9. If I bought 4, that would be £12. So this now is an expression for the total cost of buying X bottles of X and Y packets of Y. Okay, it says now in part D, using your graph, obtain the values of X and Y that give the minimum value of T. Make your method clear and calculate the minimum value of T. So this is our objective function. So if we go back to our idea that the objective function, so let's write this here, objective function is to minimize. So objective function, minimize, T is equal to 2x plus 3y. Now we can do this by observation. If we consider now picking points, what we're trying to do is minimize this. When we minimize one of our linear programming problems, we're looking now for the first point as we enter the feasible region from the origin. The way I like to do this now, we can see with a bit of observation. There's no doubt you can see with observation our possibilities. That's because it's small. What I'm going to do now is use what we call an objective line. Now our objective line is going to be T is equal to 2x plus 3y. So using the objective line, this is the method. So let's look at the lowest common multiple of 2 and 3. That's going to be 6. So if I simply set now this T to be a constant and say that 6 is equal to 2x plus 3y, what we can do is go ahead and put on an objective line. So if y is 0, x is going to be 3. If x is 0, y is going to be 2. So let's just put those on, and our objective line is going to look something like so. So let's put this on, and we'd need to label this up. So let's go through here. There it is, that's our objective line. I appreciate that this is a bit messy, I'm kind of crammed for space, but we would want to put this now, making sure that it's on our diagram. So what I'm going to do now is put this clearly on, that this is going to be 2x plus 3y, and you will need to leave that on. That now is the objective line. All I'm going to do at this point is slide it through the feasible region. You will leave it on, you will get a ruler, and you must keep this now parallel to the line. We want this gradient right here. The first now, as we go into the feasible region here, the first point of contact is going to give us our minimum value, and that will lie on one of the vertices. So let's have a look. As I go in, we can see quite clearly now the objective line is passing through the feasible region. The first vertex it gets to is this one right here. Now that's going to provide us an integer solution, so that's really good. So this is a nice exam style question. We're coming through the feasible region. That right there is the first vertex we meet. So I'm going to put this back right here, and I'm going to state now that this point right here, and let's label it up. Let's call this vertex A. We can say now, and let's just give it a different colour. So vertex A. So using the objective line, as we've entered now the feasible region, so let's put this here, we can say that it's going to be vertex A. Okay, so vertex A using now the objective line, using the objective line, and we can say first vertex or first value in feasible region. Okay, so let's write that, feasible region, just scribble that in. I'm assuming I spelled that right, pretend it is spelled right. Okay, so there we go. So that gives us now this point here. Okay, we can see now that this is going to be 4, 2. That has given us integer solutions. So what we can say then is vertex A has the coordinates 4, 2. Now, if we want to go ahead and minimize the cost, all we're going to do is sub this in. So we can say now that T will be equal to 2 lots of 4 plus 3 lots of 2. So what's that going to give me? T is going to be equal to 14. So the minimum cost is £14. That's worked out really nice. I've only been able to do that because these values are small and I've got now quite clearly an integer solution at the vertex. If you were unable to do that, what we would look at now is a simultaneous equation, and we would solve the simultaneous equation given the intersection of these two lines. So if we look at the intersection of these two lines, let's just highlight this. It's the intersection of x plus y is equal to 6 and x plus 4y is equal to 10. And this is going to be a much safer method when our graphs are not that clear. So x plus y is equal to 6, and then we've got x plus 4y is equal to 12. So let's write this here, x plus 4y is equal to 12. So this is now the intersection of the two lines, and often, or more often than not, when you're using now the objective line, it will be the solution to simultaneous equations. So let's call this 1 and 2. What we'll do is 1 minus 2, and that's going to give me now that 3y is equal to 6, which gives me y is equal to 2. If we sub that back in, we can see our integer solution, x is going to be 4. So that is the more fail-safe way. We can do it by observation. So that's what we end up with. So that's what we've got. We've got this point, and I've done it by simultaneous equation. I've done it by observation. If we were, for example, 1500 here and 1800 here, and we were somewhere in the middle, we're going to have to solve a simultaneous equation to find those points. Okay, so that's what we've done. We found the point. We found now, these, remember, are the decision variables. So we found now the optimum or optimal solution of the decision variables. We've subbed it in to find t. Remember, we're minimizing this function right here. Therefore, we found the cost of 14 quid. That's as good as it's going to get. So that's part D done. Okay, part E suggests how the situation might be changed so that it can no longer be represented graphically. Okay, what we rely on here is a 2D graph. We've only got now these decision variables x and y. Therefore, we can have an xy coordinate axis. If we introduce a third variable, z, then we'd have to make this 3D. Therefore, the graphical representation would no longer be applicable or appropriate. So all we need to state for this one suggests how the situation might be changed so that it can no longer be represented graphically. We'd have a third decision variable. Let's write this down. Third or more. Third decision variable, and you might want to write more. Third decision variable z means that we couldn't, means no longer graph, or no longer able to graph. Okay, and you might want to put a note down that it is 3 plus. So 3 plus decision variables, then we are unable to represent that. So there we go, quite a nice, fairly straightforward linear programming exam style question. It might even been a past paper question. We're setting this up, we're pulling the information out, we're looking at our decision variables x and y. The killer thing is here is to appreciate that A, B and C are not the decision variables.